So finally, we are launching into the real book content. So although it's called Lesson 3, it's actually the Chapter 2 of our textbook. And starting from today, we will be relying on the PowerPoint mostly. So I will still try to control the pace to be adequate, not too fast, not too slow. And starting from today, we are going to be based on our PowerPoint. So I try to include all the mathematical derivations embedded within the PowerPoint, but in the form of moving actions. Okay, so we can still try to control the pace. But at any time, if you have questions, do send a note to the TA. So the TA is monitoring the live streaming all the time. So if there's anything unclear, just try to send a note and we can stop and I can explain in more details. Alright, so this is probably, vector analysis is probably the easiest topic for the entire semester for you, because ideally you have been exposed to vector analysis for maybe this is the third time, I suppose. The first time you encounter vector analysis is probably in your last year of high school, if you still remember your high school years. Usually should be sweet, okay? Then the second time is you have to study the mandatory calculus, right? In calculus, you also learned vector analysis again for the second time, and this is the third time. So the reason to have vector analysis for the third time is it's very important, okay? And because it's very important, you really have to understand everything fully in details. So I am assuming you have sufficient background knowledge. It's just your memory is not that good, okay? This is contradictory. Usually young people have excellent memory, but in terms of knowledge and learning, it's not in that case. So the entire purpose for this PowerPoint set, I think I have 28 pages. But within this 28 pages, I only want to refresh your memories about the basic operations of vector analysis, and I want to emphasize on the importance of coordinate systems. Everybody here learned about coordinate systems: Cartesian coordinate, cylindrical coordinate, and spherical coordinate. But usually, no one can really memorize the conversion and transformation between two coordinate systems. And to me, that's really weird, because if you understand the fundamental well, you don't really have to memorize anything, okay? So my purpose is, I hope after this teaching, you don't have to remember anything, because like I said, your memory is very short-term. I mean, our memories are really short-term. So, but if we understand the fundamental basics, we can always derive instead of memorize. Okay? So let's start. So before we go on, we have to be very certain what are the differences between a scalar and a vector. So scalar, like a charge, current, energy, speed, these are all scalar. It's just a quantity. A vector, by definition, again, is having some magnitude, some quantity, but in addition to that quantity, you have a direction. Okay? So you have a quantity or amplitude and a direction. So, for example, electric field, magnetic field, force, velocity, these are all vectors. And today, my emphasis is another quantity is actually a vector. And that quantity is called, it's not speed, it's surface. In vector analysis, and for the entire semester of electromagnetics, the most crucial point is we have to understand a surface is not just having some area, but it's also having some kind of direction. So if we want to write this, a surface is having some kind of area plus a right direction. So this area is the so-called quantity. And the direction, it can be pointing to the right, it can be pointing to the left. Okay? So the most important key issue for the entire PowerPoint is the vector as an example to vector analysis. You have to remember, a surface is a vector. Okay, so this would be the key point for today. I'll skip these two sentences. Those are for you to read. They're easy. All right, so the pronunciation of Greek alphabets is for your reference. All right, so we are going to focus on vector algebra, how to add, subtract, multiply between 2 or 3 vectors, and then we'll go into the description of orthogonal coordinates. All right? At this moment, you can think of the meaning of orthogonal. So you can have a lot of coordinate systems, but they might not be orthogonal. Okay? So orthogonal has a strict meaning. Alright, vector algebra, we are going to introduce from the very basics. So given a vector, you can find its corresponding unit vector. Okay, as I introduce, without showing you the content, you should be answering by yourselves, what's the difference between a vector and a unit vector? And then we can introduce addition between 2 vectors and making products, multiplication. Alright, so in the PowerPoint for the rest of the semester, I am going to show vectors using bold letters, capitalized or non-capitalized, but I will have this arrow, okay? So having this arrow means you are dealing with a vector. And my tendency is, if you see some kind of vector-like stuff, but having a hat, means a unit vector. Okay? Is that clear? So if you have a vector, I like to have this arrow. If I have a unit vector, I like to add this hat. Okay? A reversed triangle. Okay. So I'll start with the introduction of a generalized vector in the Cartesian coordinate, x, y, z. So if you have a vector, it has certain magnitude in the x direction. You can also have another magnitude in the y direction and the z component. Okay? So a vector in the Cartesian coordinate, x and y and z, can have 3 different components. And each component is regarded as the magnitude in that given direction. So this is a vector. Given that vector, how do you formulate the generalized expression for the unit vector? So this is the point where you have to understand the difference between a vector and its unit vector. So a unit vector, I'm a very nice teacher. Everything I ask, I tend to provide the answer in the PowerPoint. Okay? So in the future, whenever I ask you a question, try to read and search for the answers in the PowerPoint. And usually the answer is the very first sentence. Okay? So a unit vector is a vector. It is still a vector, but with a magnitude of 1. So therefore unit, 单位，向量. Okay? So it is a vector, but having a length of only 1. Alright? So we can always convert any vector into a unit vector. So all you have to do is divide this vector by its total length. So the total length is nothing more than all the components squared, added, and they taking the square root. That's your magnitude. So the magnitude of a given vector is its total length. Okay? So all you have to do is divide the vector by its total length, and then you have the unit vector. Okay? So the unit vector is the vector itself divided by its total length. That's it. So these two vectors, the original vector and the unit vector, will have the same direction, but the only difference is in their length. The unit vector has a length of 1. Okay. I'm going very slow, and I know you know this already, but we are trying to build our knowledge on the very fundamental knowledge. Okay? On the very fundamental point. Alright, vector addition and subtraction, I think you already know that. So if we have vectors A and B, we want to add between them. In adding, you have to move like B. So the starting point is connected to the end point of another vector, so then you can add. Right? So A plus B vectors become a new vector C. Right? So now the question is, we understand how to add, how to subtract between two vectors. For example, if I know vector C, C minus A equals to B, right? You can move around. A plus B equals C, so you can move B to the left-hand side, so C minus B equals A. So what I'm trying to say is, when you add between two vectors, you have to have the vectors connected in some kind of series or cascaded. Okay? So the start to the end, start to the end, so you add. But when you subtract, remember, when you subtract two vectors, you have to have the starting points meeting together. For example, C vector minus A vector, the starting points of the two vectors are now coinciding. They overlap. Then you make the subtraction. And the direction is C minus A, so the resulting vector is pointing towards the first one, equals B. And the direction, remember the direction points towards the first guy. But these are already covered in your high school and your calculus. What I care more about is, throughout the semester, you will be performing a lot of vector calculations, making multiplications. Adding, subtracting is not that a big deal, but multiplication is more complicated. So there are two basic vector multiplications. The first one is called the dot or the inner product. Inner product. Okay? So now you are given two vectors, A and B, randomly. Okay, just randomly. So usually if you have two vectors, each one is having its own length and direction. So usually A and B are not equal. In a sense, they don't have the same length They don't have the same direction. So as a high school student, all you have to do is, well, you have to try to find the angle between the two vectors, theta AB, right? So once you know the angle between the two vectors, you can just do the inner dot product by calculating the length of vector A multiplied by the length of vector B, and then multiplied by cosine of the angle between the two vectors. So that's what covered in your high school years. But now you are a second year or third year university student, you should learn more. So what is the physical meaning of vector dot product? So you're given two vectors, right? And some mathematical manipulation asks you to perform the dot product. But what does it mean? After two vectors making a dot product, what does it stand for? Again, I'm a very nice teacher, right? I always provide the answer in my slide, and usually it's the first sentence. So as you can see, even though what I'm trying to teach today is purely mathematics, I am still trying to bring out the physical meanings behind all these mathematical operations. So we're not here to learn mathematical derivation, we're here to learn what messages are hidden behind the math. Okay? So the dot product, or the inner product, actually means the projection of one vector onto the other. Okay? So you have two vectors, A and B. So if you make the projection, what does projection mean? For example, you have a light. You have a light somewhere here, and you shine the light. Because you have vector B above vector A, so imagine vector B is blocking the light. Okay? So you will see this part being bright, but this part being dark, because light is blocked by B. Right? So this segment in red is called the projection. How long of the distance or the length on A is being blocked by vector B? That's called projection. Okay? Another way to explain it is making a dot product between two vectors is trying to find out how likely they are. How likely they are, or how much in common they are. So for this case, if you want to maximize the dot product between A and B, how should B and A be related? If you want to maximize the dot product, what is the necessary condition for A and B to be? They should be in parallel, right? They should point into the same direction to maximize it, which means in the language that you can understand, theta has to be 0, right? To maximize the projection length. So in the best case, if B and A are parallel in the same direction, then the projection is basically the length of B, right? The projection. Okay? So, after the introduction, so whenever you have two vectors making an inner product, you are trying to sense how common they are. Do they share components in the same direction? And the result is a scalar. It's only a quantity. Because the projection is the distance, it's only scalar quantity. So if you want to maximize it, the two vectors should be parallel. Okay. So if you want to minimize it, how do you minimize the projection? They're parallel, but they're rotated by 180 degrees, so they are anti-parallel. Okay? So theta AB is pi, 180 degrees, so you minimize the projection. How do you make the two vectors unrelated? Nothing in common. They're like strangers. Meaning you want to have A dot B equals to 0. Theta has to be 90 degrees or 270 degrees. They are perpendicular. Okay? But in summary, when you try to perform dot product, when you're trying to find the inner product, you're trying to find how likely they are in common. Okay? And the result is a scalar quantity. Right? Since A dot B is a scalar quantity, there's no direction involved. So A, B, they can dot A dot B or B dot A, doesn't matter. So they can commute. Okay? And they are also distributive, but this you already know. Let's come to the cross product. But usually cross product, you don't have a good feeling to it. The calculation is more complicated. So when you have two vectors and you want to perform the cross product, YG. Okay. What you learn during high school is, well, A magnitude multiplied by B magnitude, now is sine theta. Okay, now it's sine theta. But then you have a unit vector before it. So what does that tell you already? The dramatic difference between cross product, which is also outer product, as compared to dot product, is the result of the cross product is still. So now you have to be very careful, because A cross B is a vector. It has its own magnitude, a scalar quantity, plus a direction. So be very careful. A cross B, usually we use the right hand rule. So A cross B gives you the direction. The resulting vector direction is pointed by your thumb. And the result direction must be perpendicular to both A and B. Okay? So what does that lead to you? What does that imply? You make an A cross B, the resulting vector C, or whatever, A cross B, are perpendicular to both A and B. So the meaning is most related to what I mentioned. The main point for this class and this PowerPoint is to let you know surface in vector calculus is a vector. So surface is very related to A cross B. So let's come back. A times B times sine theta is basically saying that the A length and multiplied by this segment, right? B times sine theta. So this is your base and multiplied by the height. So that gives you an area, right? An area. And it also gives you a direction. So whenever you're trying to perform the cross product between two vectors, what you're really trying to do is you're trying to define a surface encompassed by these two areas. by these two vectors and with the right direction. So what you're trying to calculate is the shaded region. That's an area encompassed by vector A and B, right? The shaded area, but then you have a given direction. So the result is a surface. So remember, again and again, I must warn you, a surface in electromagnetics, in calculus, is a vector. Okay? So you might be wondering, oh, I have this surface. Can this surface be the same, identical, when you calculate it by A cross B or B cross A? Is there any difference? In the past, you learned a surface by its area. So it's a scalar quantity, you don't care. A cross B, B cross A, you don't really care. But now you have to be extremely careful. In electromagnetics, area, again, is a vector. So A cross B is having this area, but then you have the direction. This direction is very sensitive to the order of the vectors. So using the right hand, A cross B points up. But if you perform B cross A, in this case, your thumb is pointing downwards. Okay? So this same area, same surface, with the same area, the magnitude of the surface will be the same, but the direction will be opposite. This is extremely important for all the mathematics and all the calculations afterwards, because if you still remember, you learned divergence, you learned curl. All these are directional sensitive. So I'm putting a lot of time on the introduction of curl because this is the very first example. We're dealing with real vector quantities. Vectors come in with a scalar magnitude, which is not direction sensitive, but the direction really depends on how you perform the curl. Okay? So therefore, A cross B is not equal to B cross A. If you take the absolute value of A cross B and B cross A, they are the same. They are the area of the two vectors. They are the same. But, as I mentioned, the surface comes with area information and directional information. So the directions will be opposite. So cross products do not commute. Okay? So then you can read the next two. You can try to use your right hand. Okay? A cross B points up, B cross A points down. The resulting vector are both orthogonal to both A and B. But A cross B is opposite to B cross A. Be careful, right? So as you can see, I'm going extremely slow, even though I'm using purely part point. But my hope is, like I said, on the first class, probably you're in engineering department because you don't like math and you don't like calculus. So please, make this your last time in learning. I don't want to see you again next year.